Last video in this lecture series, we'll do two quick examples. So for the first one, we want to try to rewrite this function f as, I'm going to think of it as phi of z over z minus I cubed. And I'm thinking about phi of z here is just the numerator, z cubed plus 2z. And let's realize that phi of z is a polynomial. It's entire. And furthermore, let's check when you plug in I, phi of I is I, which is not 0. That's critical. You have to be analytic at the problem point, at the singularity at I, and you can't be 0 there. So we're good to go. Here's a problem where it is what it looks like. This looks like a pole of order 3, and in this case it is. We've seen other problems where it looks like a pole of order 2 or a pole of order whatever, and in fact it isn't. So be careful. But in this case, because the numerator is entire and it's non-zero at I, we're good to go. And so we can go ahead and say thus f has a pole of what? Order 3 at z equals I, and we'd like to compute the residue at I. So with the residue at z equals I of f is going to be equal to the second derivative of phi evaluated at I divided by 2 factorial. Well, the second derivative, let's see. So we're going to get 3z squared plus 2, so 6z, so 6i over 2, so we get 3i for the residue. And that's a pretty slick way to get your hands on the residue right there. Certainly beats having to look at the Lorentz series in this case. All right, so last example. Whoops, I erased it. Oh, man. That's all right. I've got it here. So let's do f of z equals the sinh of z over z to the fourth. And so what we want to do is do the same strategy that we've been doing. We want to say, okay, this looks like a pole of order 4. I'm not sure if it is. Let's break it up in the right way and think about it. So we can think about f of z as some phi of z over z to the fourth. And our candidate for phi of z is going to be sinh z. Certainly sinh z is analytic at 0. But the problem is phi of 0, which is sinh of 0, is 0. And so that's not the right phi. This doesn't work. So you can't conclude f has a pole of order 4 at 0. And in fact, it doesn't have a pole of order 4 at 0. So how are we supposed to see this? Well, I think the easiest way to see it in this case is to look at the Lorentz series and figure out what the order actually is, what's actually happening from the Lorentz series, and then we're going to go back and work our way backwards and see how the theorem is still true, because it doesn't feel true right now, right? It feels like it just failed us. So do be careful. In this problem, if you're just not paying attention, you might think that, oh, phi equals sinh z, pole of order 4, I can compute the residue, and you'd get it wrong, actually. So looking at the Lorentz series, we can say, okay, sinh z over z to the fourth. This is 1 over z to the fourth. Let's write down the series for sinh. So z plus z cubed over 3 factorial plus z to the fifth over 5 factorial plus so on and so forth. Okay, so this is exactly 1 over z cubed plus 1 over 3 factorial times z plus what? Z over 5 factorial. That's all we need. I'm not going to write any more down. And now at this point, because I've got the Lorentz series in front of me, I know exactly what's going on now. Now I can say, so f has a pole of order 3, right? You can see that, pole of order 3. And in fact, we've got the residue as well. The residue of, at z equals 0, of f is just 1 over 6. All right. So how does the theorem play into this game? So the theorem says if you have a pole of order 3, then we can take our original function, which was sinh z over z to the fourth, and we can write this as some phi of z over z cubed. I have a pole of order 3 at 0. I can do that and write this as a function with the function phi, where phi is analytic at 0 and phi of 0 is not 0. So how does one go about doing that? Well, the suggestion here, the algebra here, if you just solve for phi, you come up with phi of z is sinh z over z, and you might say, well, gosh, that's not analytic at 0. That has a singularity at 0. What if it's a removable singularity? Let's see. Well, in fact, that's exactly what it is. So sinh z over z, when you look at the formula for the Lorentz series for sinh, this is 1 over z plus z cubed over 3 factorial plus z to the 5th over 5 factorial plus so on and so forth. You get 1 plus z squared over 3 factorial plus z to the 4th over 5 factorial plus so on and so forth. So you know how you should define sinh z over z at 0. In fact, this is telling you phi of 0 is 1. Right? When you plug in 0, these are all gone and you're left with 1. So the theory actually allows you to predict without looking at the Lorentz series. You know that this function is gonna have a removable singularity at 0, because you know that there's a way to write this as some function phi that's analytic at 0 and non-zero at 0. And that's exactly what happened. So the theorem is still true. It just didn't work the way that we initially expected it to. At our first glance, we expected sinh z to be our phi, and in fact, that's not what phi is. So I'll end this series here. The homework is posted. This homework for, I think we're on lecture 5 now, is not due until Friday, so you've got a shorter assignment due on Tuesday and then another assignment due Friday, and I'm planning on one more assignment due the last week of classes. So we're almost there. You guys are doing great. Keep in touch. If you need anything, always feel free to reach out.